The first of the colligative properties was vapor pressure lowering, which is Raoult's law. But now what we're going to do is talk about what's much more helpful to chemists most of the time, honestly, which is changes to the boiling and freezing points of different solutions. And we're going to again focus on the solvent in these, but it's an amazing kind of process, and it is related to the vapor pressure. First, just some definitions. Boiling is where the solvent begins to go from the liquid to the gas phase. And condensing or freezing is where the solvent, which is a liquid, will start to go into the solid phase. So boiling and freezing. As you put solute in a solvent to make a solution, we're going to see that the boiling and freezing points will change. And they're changing by an amount delta T. And delta is the difference between the boiling point of the solution and the boiling point of the pure solvent. Or if it was for freezing, it would be the difference between the freezing boiling point of the solution versus freezing point of the solvent. Here's one thing that's going to be really important. Your delta T should always be positive, all right? Don't use negative delta T's. It just gets too confusing. In some books, there's a constant K that's given, and if the K values are negative, then that's where the delta T's are negative. But it just makes your life so much easier if you always remember to have a delta T which is positive, all right? So in the case of boiling, then, to get a positive, boiling points we're going to see are higher. It would be the solution minus the pure solvent. But for freezing points, it's usually better to do the solvent minus the solution. We'll talk about that here in a little bit.
At 30 degrees Celsius, pure water and a solution of ethylene glycol have nearly the same vapor pressure. As temperature increases, so do both vapor pressures. But when the vapor pressure of water reaches 1 atmosphere, ethylene glycol is at almost half that. Pure water boils at a significantly lower temperature than does the ethylene glycol solution.
This video shows the effect of having an ethylene glycol solution versus pure water. And we're looking here at the normal boiling points. Now, water has a normal boiling point, which is where the vapor pressure equals 1 atmosphere of pressure. It has a normal boiling point of 100 degrees Celsius. All right, no problem. However, if you have a car radiator, it's easy to get to a temperature that's more than 100 degrees Celsius, and you may not want your water to start boiling. So what people will do is they'll put some kind of antifreeze in it. Ethylene glycol is one possible antifreeze. There are a couple different ones that go in there. But anyway, the red curve then is for a solution. And solute molecules, which in this case ethylene glycol, are blocking the solvent water molecules from going to the liquid to the gas phase. So what that means is your vapor pressure, the y-axis, is lower. All right. So at the same point there, you can see that the solution, roughly that point right there, that solution has a much lower vapor pressure than you would have at pure water. So if you keep going on the red line over to that point, you can see that the solution then has a boiling point which is more like 115 degrees. So what this means, your boiling point of the liquid, the solvent, will be higher in the solution than it was with the pure solvents. So we'll talk here in a little bit about how boiling points are elevated. Boiling points will be higher in a solution than they will be if you had pure solvent. So water boils at 100 degrees Celsius. Ethylene glycol plus water will boil at 115 or so. Now, for boiling point elevation, to figure it out, delta T, which is the boiling point difference between the solution and the solvent, delta T equals K times M. And K is just a constant. You never have to worry about it. There's a value for water over here we'll talk about in a second. I will give you those K values, or you can look them up and stuff, no problem. But little m there is molality. So molality, moles of solute over kilograms of solvent. And from this point, you can figure out how much higher your boiling points will be, stuff like that. So in this example, let's use that ethylene glycol in water example again. 62.1 grams, which was 1 mole, in 250 grams or 0.250 kilograms of water. And the question is, what's the boiling point of the solution? Now, you do have to look up a K value. K values are based on the solvent. So this is water, no problem. The value is 0.512. The units are weird. Don't worry about that. Molality will be moles of solute over kilograms of solvent. So that's 1 mole of ethylene glycol divided by 0.250 kilograms, 4.00 molal. We calculated this earlier, no big deal, but just a good refresher. And we need this value because delta T, the change in the boiling point temperatures, equals that weird K constant times the M. So when you calculate it then, 0.512 times 4.00, delta T 2.05 degrees Celsius. And what this tells you then, water normally boils at 100 degrees Celsius exactly, and you add that delta T to it, your solution will boil at 102.05 degrees Celsius. So again, higher than the boiling point of the pure solvent will be. So delta T equals K times M. You have to calculate M to find delta T. K values you can look up or I'll give them to you, no big deal. Freezing points have a very similar looking expression, but freezing points, of course, are lowering instead of raising. And what's happening in freezing points is those crazy solutes are blocking the solvents from going from the liquid to the solid phase. But the equation looks really similar. So delta T equals K times M for freezing point lowering, just like delta T was K times M for boiling. But remember, at freezing point, the solution will be lower while a boiling point will be higher in the solution. So delta T, which sometimes gets a little symbol F instead of B for freezing versus boiling, it's the difference between the freezing point. K is just a constant. It's a different constant than you have for the boiling point. So you have to look up a different thing, but again, you don't need to worry about that. And little m is molality. So I want to show some videos here on the right that shows what's happening in freezing with a pure solvent versus a solution. And in this video, they use pure water on the left and a ethylene glycol water solution on the right. But one problem with this video is that it shows the ice as being more dense than the liquid water, i.e. your ice cubes sink to the bottom. And as you know, by putting an ice cube in water, the ice will float on the water. It's less dense, hydrogen bonds, we talked about it, et cetera, et cetera. So the videos aren't perfect, but the idea is really valid. Most compounds, the solid phase is more dense than the liquid phase, so this would be legit, but it's not legit with water, alas. But anyway, let's see how this works here, and I'll talk about it.
When water freezes, its molecules leave the liquid phase and attach to other molecules in the solid phase. At the freezing point, an equal number of molecules move into and out of the solid phase. A solution of ethylene glycol, automobile antifreeze, has a freezing point lower than that of pure water. Molecules of the solute block the interface between the solid and liquid phases, thus decreasing the rate at which molecules leave the liquid phase and attach to the solid.
So on the left-hand side again, except for the bad thing about ice sinking in water instead of floating, but same idea if it would float, by the way. But anyway, you have a constant equilibrium between liquid molecules going to the solid phase and solid phase molecules breaking off and going to the liquid phase. And that's what freezing is all about. However, when you have a solute, the ethylene glycol, those little yellow atoms on the right, they once again are acting as bouncers or blockers, and they're preventing the liquid from going to the solid phase. They don't care about the solid going to liquid phase. That's not a problem, but the liquid going to solid phase is definitely important. So if they're blocking it, you have to lower the temperature quite a bit to make the liquid molecules continue to bond with the solid. So the punchline here is that a solution will have a lower freezing point than that of the pure solvent. So if water normally freezes at 0 Celsius, the solutions might have a freezing point of, say, -5 degrees Celsius, something lower than that. So it's pretty cool. So a solution will have a higher boiling point than a normal solvent. It'll have a lower freezing point than a normal solvent, and it will have a lower vapor pressure than the regular solvent. Here's an example of a freezing point question, and again, it's very similar to the boiling point. It's going to be another delta T equals K times M. We will use a different K value. Freezing point constants are different than boiling point, so this would be something you'd look up. I highly recommend that you let your delta T be a positive number all the time. So let's figure out the freezing point of our 4.00 molal ethylene glycol water solution we've been using so far. No problem. Delta T equals K times M. It's that weird freezing point constant times 4.00 molal. The delta T, 7.44 degrees Celsius. Now, you have to remember that water, which we'll use a lot, 0 Celsius. And this shows how much lower the freezing point will be relative to the pure solvent. So what that means here is that the freezing point of the solution, 7.44 degrees less than 0, minus 7.44 degrees Celsius. Now again, a lot of times books will use negative KF values because they think you should calculate a negative delta T, etc., etc. I wouldn't do that. I would just make your delta T positive all the time. If you get a negative number, just absolute value it. And absolute value your K value if you happen to run into a negative K value. Molality is based on mass, grams, moles, that kind of stuff. And in chemistry, mass can never be negative, all right? So molality must be a positive number. So if you really want to do delta T is negative and K is negative, that's fine. Just make sure that your molality is a positive number. It can't be. But again, what I would do, delta T, just make it a positive number. You have to realize it's going to be lower than whatever the freezing point is. Not too bad. So in this question, we have the following aqueous solutions, and you want to know which one's going to have the highest freezing point. And pure water, sodium chloride, sugar, sulfuric acid, blah, blah, blah. And delta T equals K times M. K is based on the solvent. They're all supposedly water. M is the molality. So in one way, it might be tempting to say answer D because that's the highest molality. But remember, freezing points are lowered in solutions relative to the solvents. So the higher molality would have a lower freezing point. Boiling freezing points are being lowered. So when you think about this long enough, this is a trick question. The pure water will have a higher freezing point than all of the other ones, all right? Because the water, the pure solvent, always has higher freezing points than the solutions that are made from it. So in this one, water will have a higher freezing point than all of the solutions and stuff that are there. Freezing points are lowered in solutions relative to the pure solvent. Keep that in the back of your mind. At this time, it's worthwhile to remember that ionic compounds will dissociate. They don't just dissolve, they dissociate into their ions. And because these colligative properties depend on the number of particles, this becomes important. So sometimes you see an extension to all the laws we've seen so far where they have what's called the Van Hoft factor, and it gets the symbol I. So as an example for the freezing point we just did, delta T equals K times M times I, where I is the Van Hoft factor. Now, so far in all the examples we've done, all of our compounds have been covalent. And covalent compounds, nonmetals and nonmetals, you don't have positives and negatives pointing it out, and that's why I've used them intentionally. However, you can absolutely use ionic compounds as well, as long as you consider the Van Hoft factors. So if you have a covalent molecule, I is 1 all the time. So ethanol and acetone and DNA and caffeine and all these things that, sugar for that matter, all the things that dissolve in water that have nonmetals and nonmetals, covalent bondings, they all have just 1. However, sodium chloride breaks up into Na plus and Cl minus. 2 particles, 2 ions per NaCl. So the Van Hoft factor would be 2 because you have 2 pieces for every NaCl that breaks up. That's why your I factor is different. Now for magnesium chloride, you'd have a magnesium 2 plus and 2 chlorides in solution. So 1 magnesium and 2 chlorides, 3 pieces total. I factor is 3. So notice that you're adding up the number of ions to find the I factor. Aluminum chloride would be 4 because you'd have aluminum and 3 chlorides for 4 particles total. And it does affect freezing points, boiling points, stuff like that. Here's a question you might see. It says, how much sodium chloride have to dissolve to have in 4 kilograms of water to lower the freezing point to minus 10 degrees Celsius? And there's the Kf value again for it. So delta T equals K times M times I. Now, delta T is going to be the difference between pure solvent and the solution. I'm going to absolute value it. So 10 degrees lower would be a 10 degrees delta T positive. And so in this case then, delta T would just be 10. NaCl breaks up into Na plus and Cl minus, 2 ions per NaCl, so I is going to be 2. And we have the K value there, so let's use all this information to calculate the molality, which is this number right here, 2.68817. That's the moles of sodium chloride per kilogram of solvent. It's the molality that we solve for there. And if you multiply moles over kilograms by the kilograms of solvent, 4.00 kilograms, then that gives you the moles of the NaCl, which is this number. Multiply that by the molar mass of NaCl. It's going to take 628 grams of NaCl in 4.00 kilograms of water to lower the freezing point by 10 degrees. So this is just another twist of things. Now, we won't do tons of things with ionic compounds in water for colligative properties, but you might see one. So if you see one, just remember that I factor can be pretty important, and it's easy to figure out. You just literally count up the number of ions, that equals the I factor, no problem. I should note that we are only going to use what's called a theoretical I factor in Chemistry 222 and Chem 223. Sometimes there are actual I factors that are thrown around. If you see one, then definitely use it. But for us right now, we're going to use what's called theoretical, and that's where the number of ions literally equals the I factor. So in this question, it says which one will have the higher boiling point? And there's pure water, there's the sugar, and there's the NaCl. All right. Well, delta T, which is the change to the boiling point, equals K times M times I. Remember that. Pure water should have the lowest of the boiling points. All right, boiling points will get higher in solutions, not lower. So answer C is out. And then if you look at those two molality values, well, 0.15 molal for sugar is higher than 0.10 for sodium chloride, and it might be tempting to say the sugar is higher. Higher M should give you higher delta T, which is bigger boiling points. However, sugar is a covalent molecule. All carbons, hydrogens, and oxygens, I factor of 1. But sodium chloride is ionic, and in water it's going to break up into Na plus and Cl minus, an I factor of 2. So the I factor times the molality is what we should consider here to have the higher boiling point. So for sugar, that would be 0.15 times 1, which is just 0.15, and that's high, but it's not as high as 0.10 times 2, the I factor for NaCl, for sodium chloride. So in reality, answer A, the 0.1 molar NaCl should have a higher boiling point because of the I factor. So this is why those sodium chloride I factors can be pretty important. Just consider them in the back of your mind as you go through these problems. The best use of colligative properties, and honestly why we're talking about it more in this section than anything else, I guess, is because colligative properties can be used as a way to find the molar mass of the solute, and this is huge in chemistry. So finding the molar mass is really important. Allows you to go grams per moles, you can do limiting reactants, etc., percent yields, all that kind of jazz. So finding the molar mass is big, and there's a lot of instrumentation that does it, but it's also nice to have a chemical method to do it. So let's do an example here of how you can find the molar mass for a boiling point solution problem. So in this problem, all right, we've got this compound called azolene, and azolene is being dissolved in benzene. And by the way, these are both organic compounds, covalently bonded, so we don't have to worry about any of the I factors. But anyway, we're putting this azolene, 0.640 grams, in 99.0 grams of benzene, and the boiling point of benzene benzene, which was 80.100 degrees Celsius, goes up to 80.230 degrees Celsius. Not a big amount, but it is enough to allow us to find the molar mass of azolene. So let's figure out how this works. So delta T equals K times M times I is the big expression. Well, delta T is the difference between the boiling points. And when you do that for benzene here, it comes out to be 0.130 degrees Celsius. Now, I is just 1 because these things are all covalent. We don't have to worry about that. And also, we have the K value there. It's a KB value. Oops, that says KM. That's a typo. Sorry about that. It's a K value. That's the important part. You don't need to worry about B's and F's like I do, obviously, as your instructor. Prophet back on. Anyway, we can solve for M. That's the idea. M is the molality. It's delta T over K times I technically, but I is just 1, so who cares? When you figure this molality out, 5.14 times 10 to the minus 2 moles over kilograms. Now, moles is going to be moles of solute, moles of azolene, and kilograms is going to be kilograms of solvent, kilograms of benzene. So if you take the molality and you multiply by the kilograms of benzene, 99 grams divided by 1,000 is 0.0990 kilograms. Kilograms times moles over kilograms gives you 5.05 times 10 to the minus 3 moles of solute. And that's moles of azolene. Well, we had 0.640 grams of azolene in this problem. So that grams divided by the moles we just calculated, 127 grams per mole is the molar mass of azolene. And this is a real cool way to kind of verify that the compound's molar mass that is using is the same as you think it is. Sometimes it's nice to have a physical method to balance the electronic methods that are used so often as well. We're going to use this expression quite often, and so a quick and dirty calculation, a way to find the molar mass for a problem like this, which by the way can be used in both boiling points and freezing points, is molar mass equals grams of solute times the K factor, whatever it is, divided by the delta T and the kilograms of solvent. So see if you can use this to get the 127 grams per mole number out. It certainly is a lot less work. It's one-stop shopping instead of doing it piecemeal, which is what we did right here. This also assumes, of course, that your I factor is 1. If you didn't have an I factor of 1, you could multiply the K by I to figure that out. But anyway, it's a nice kind of way to do it, and it might help on our lab coming up.